We are live on LinkedIn and YouTube. And our topic today, very special topic, nuclear power waste. And with us, thank you for coming, Gabriel Lynch Murphy. He has a fantastic resume, and I put some of his points here. Leader of nuclear waste disposal, solid state chemistry researcher, and several other things, postdoctoral nuclear materials scientist. Welcome, Gabriel. Thank you for coming.
Thank you, Armando, for having me. I'm very happy to be here today.
Yeah, it's a pleasure. Please, Gabriel, let's start talking about a little bit about the nuclear waste remain radioactive. How long it takes? 100,000 years? Is it true?
Yeah, sure. I mean, I think it's a very kind of complicated question because there's firstly kind of many kinds of nuclear waste to talk about. In the nuclear industry, you talk often of high-level waste, intermediate-level waste, and low-level waste. And so it's best to kind of first break them down into each one what they are. So going from, say, bottom to top, there's low-level waste. And so this is often things which is like kind of like gloves, this is lab coats, this is medical equipment, so often hospitals. Radionuclides are used very, very often for treatments, for instance, for imaging, and also for, say, cancer treatments as well. And so the gloves and kind of the disposal wear is often considered low-level waste. And this is stuff that has minor contaminations of radionuclides on there as well. So very, very, very short-lived things. And that waste is typically only lives for a very couple of years, let's say, in terms of harmful radiation. The next level is what's called intermediate level waste. And so, of course, as the name suggests, this is a bit higher. This is to do with things that we say are sort of medium-lived or shorter-lived radionuclide isotopes. So again, the hospital example is quite good as well, because you can look at things like technetium, which is quite known as a radioisotope used to treat cancers, and imaging as well too. Technetium has a half-life of a bit longer as well too. And so for things like technetium or cesium or strontium, these intermediate level wastes have half-lives around 100. Well, they have disposal times around 100 years. So when one wants to dispose of intermediate level waste, as I say, arising often from hospitals, also from the nuclear industry and power sector as well too, it's around 100 years. And the final one, which is what's most important, which is often what most concern for people, and it's more to do with the nuclear energy sector itself, is high-level waste. So high-level waste is often to do things what are called the actinides. And what the actinides are in terms of chemistry is elements like uranium, elements like plutonium, elements like curium, things like this. These are things that come out of spent nuclear fuel and out of nuclear energy production. These live much, 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 much longer. They take thousands and thousands of years to decay right down their decay chains. And they also present much more of a significant hazard because they have much more of a stronger radiation field coming off them. And so in many ways, when we talk about radioactive waste disposal, these are the three categories. And as a consequence, they're approaching different avenues and different severity. But the last one is probably the most significant one.
And how about volumes and weights involved in these operations?
Sure, I'll give you some examples for this too. So I work in Germany, and I essentially work for the German government, the German taxpayer, and so my job is to support currently Germany's disposal of its spent nuclear fuel and its nuclear waste. So in Germany, it's been operating nuclear power since around the 1960s, and it ended nuclear power in 2023. And so if you look at that in terms of time scale, you're looking at around sort of 60 years of time. And in that space, it's generated around 10,000 tons of spent nuclear fuel that needs disposal. And so at one sense, that sounds like a large number, but if you kind of put it into scale across other energy forms, it's very small. So for instance, per year, Germany emits around, I believe it's around 100 million tons of carbon dioxide into the atmosphere. And that's just arising from cars, that's arising from the coal industry, from the gas industry as well too. So when you compare what Germany has generated over 60 years of nuclear energy production, which has supplied, well, carbon-free electricity, safe, dependable electricity for many, many years, the amount of actual waste is actually quite small. And this is a consequence of just sort of the nature and the science of nuclear energy, in that the energy density of nuclear fuel is extremely high, therefore the amount of waste is actually quite small.
Great. We have some questions. One of them is from our audience, is about nuclear leakage, but I will postpone this point a little bit because I would like to know from you before that uh, the process of protection, the treatment of this waste. How are these directions, and what the impacts that can have when it in case of fails of this protection.
Sure. Well, maybe I'll take a step back and we talk about kind of how nuclear waste kind of generates. So if we talk about spent nuclear fuel and what comes out of a nuclear reactor and treating it. So the first thing is nuclear fuel sits in a nuclear reactor for around 12 to 24 months. So it generates energy for 12 to 24 months and it just stays there. It gets hot from fission, heat is extracted, spins turbines. And from that, after 24 months, it's then removed during a fuel reloading cycle, which takes around sort of 6 weeks at a normal power reactor. Once that fuel is removed, it's taken to these cooling ponds. And maybe people heard about these cooling ponds when they talk about reactors around the world too. But these cooling ponds, the fuels will sit there for typically a couple of years while they cool down because the fuels are very hot. They're still undergoing fission. They're still actually generating a form of thermal energy, but they need to essentially cool down. So that's the first step of the waste process for spent fuel too. After it's cooled down significantly, they're transferred into containers. So they go from what are called wet storage, because in these ponds, they're surrounded essentially by water. Water is actually quite a good way to slow down neutron production, actually slow down the emission of energy from the fuel. And so once they've cooled down enough, thermally cooled down, I mean, so typically depending on the country, the temperature requirement, say in Germany, is it has to be less than around sort of, I believe it's 400 Kelvin. So less than sort of, let's say 250 degrees Celsius. So that then material is then transferred to what's called dry storage. And so it's transferred often using robotic cranes and robotic arms to these large containers. And so they're called casks often. A nuclear fuel rod assembly is around 4 meters long, and they're very, very thin little pins, very, very thin little column of pins, and a kind of square rectangle assembly. So this 4-meter bundle with some other bundles is picked up, it's moved, and it's transferred inside this caster. Once inside the caster, the safety precaution of the caster is they're often very, very, very thick. They're thick stainless steel, but in addition to some other safety measures. But the external radiation dose coming off them is such that it is minimal. People often see on social media people standing next to these casters and putting their hands against them because they're designed such that the dose coming out of these casters is prevented. And so at that point, they have a hard seal on them, so to ensure there's no escape of radionuclides from the caster itself, nothing's going into the environment. And these are then often stored. Once they're in that storage, the final task is then eventually take it to a repository. And this is often the most difficult task, particularly from a political sense, which is actually find a place where these things can be left for a very long amount of time. But this is called one method, to be fair. So this is the method in Germany. It's called Deep Geological Repository option, in which the plan is it will be essentially placed in a geological repository for thousands and thousands of years with several engineered barriers around it to make sure no one can get to it and it can't get to anyone else. But at the same time, there are options as well to treat the waste, because this is not a very efficient way, because this is essentially what we call direct disposal. When you generate nuclear waste, you're only actually around 5% of the nuclear fuel is actually used. So there's 95% in the fuel rod sitting there that has not undergone fission, that can be recycled and can be repurposed. So in some countries, for instance, like France, very famously, they actually do what's called partitioning and separation, where they actually extract radionuclides and they extract the fuel out and they recycle it back around. And so they can keep recycling the fuels around and around, move them back into reactors, back to generating energy. In many ways, as some people argue theoretically, you can almost find it as an endless source of energy.
Very good. Let me put the question from the audience. Is Leakage, I don't know exactly how to pronounce this question. Can you provide some information about nuclear leakage in Pakistan? Is there one?
I'm not sure I could give us specifics about Pakistan. I mean, Pakistan is very famous. Pakistan is quite big, particularly nuclear weapons, and they're quite political on the news these days too, with the issues currently between Pakistan and India. But I can't say too much about the Pakistan nuclear program as well. I mean, it is known that they are not very well tracked by the International Atomic Energy Agency. They are tracked, of course. They definitely have people have their eyes on them to make sure they're doing things that are of good substance. But as opposed to other countries, say in the EU or United States, there's less safeguards apparent. So I can't say too much about them, just that there are often a few questions raised about them.
Very specific one. What are the most effective and common long-term solutions to store high-level nuclear waste?
So currently the most, let's say, in use would be direct disposal, as I say. So actually transferring to a final repository. This is still kind of a new thing. So the most known in-use example would be in Finland, where they've actually constructed a repository and it's about to enter operation next year. So to my understanding, they're transferring spent fuel there right now, and it's going to be sealed within the next 5 to 6 years. And so once that's sealed, it's going to be monitored, I believe, for about 100 years, and then eventually the whole site will be essentially closed off, and it'll essentially just become almost just a remnant of the Earth. It's engineered so well that it's not expected that any radionuclides or any material will be released for the next sort of 100 to 100,000 years as well. Mm-hmm. So this is often considered the best solution in many ways, or the most direct as well too, namely because there's often other solutions in terms of reprocessing require a bit more complexity in terms of the engineering.
Public perception about and acceptance for nuclear energy as a clean energy source is not good. It's associated to waste, to bombs. What exactly happens in this case?
It's a complicated issue with nuclear energy, nuclear waste, nuclear weapons, because there are many contributing factors to why nuclear, let's say, has a bad rap. You know, if one looks in the 1950s and 1960s, nuclear was just the future for everything. The Soviet Union wanted to make planes or experimental planes out of nuclear engines. There's many ships that were built using nuclear engines. There's ideas to make cars with nuclear engines, because the idea, which is still quite true, I argue, is that the energy source is quite unlimited. I mean, even now you can look at things like the Deep Space Voyager space capsules, which have radioisotope emitting generators on board that are based on plutonium isotopes as well too, and these still power the Voyager missions deep into space. But in terms of the perception, essentially what's happened is, in my opinion, it's often an intergenerational issue. So the first thing, of course, was the Chernobyl nuclear disaster, which shed a very, very bad light on nuclear energy and nuclear waste. So it's a lot of people had understandable fear. The second problem too is the complexity of nuclear, because radiation and radionuclides, they're hard to often comprehend because the inherent danger of radiation is invisible. You can't actually see it. It's very hard to actually know you're exposed to radiation without actual appropriate equipment. Geiger counters is the famous example for it. And sort of as a consequences through the years, there's often been sort of almost an intergenerational issue where, of course, the negativities of Chernobyl flow through from the 80s to the 90s to the 2000s, and this is kind of flow through public perception. At the same time, many countries, I argue, have not been very good at the communication of the benefits of nuclear. And you can see this too. I mean, you can look at countries, I believe, like sort of Finland and Sweden, where the Greens parties there are quite... they have bipartisan support towards nuclear energy. They see it as a part of the future of green energy and stable carbon-free energy. But if you look, say, in Germany, even some other countries too, like Australia, where I'm from, the Greens parties there have quite the opposite opinion as well too. So there's often a sway between, and it's based on kind of the legacy as well. France always has had as always, the example people point to in terms of where it's been kind of very positively shown, because in the 1980s and the 1990s, France upscaled a lot of its nuclear because they were after strong energy sovereignty. And in these days too, after the gas crisis caused by the Ukrainian-Russian war, many people are looking again to nuclear as a way of getting energy sovereignty and energy security as well too. So in short, the opinion has changed, but there are intergenerational issues again associated with what's happened with Chernobyl and Fukushima, what's happened with politics as well too, poor communication, and often just misunderstanding of what nuclear is and the benefits that can arise from it.
Yeah, and politics interest that we cannot survive with this. Are there countries that export nuclear waste to other countries, and they both accept this deal? or not?
There's a lot of different deals around the world of how this has been done. I mean, some countries have it in their law that they are not to ever accept nuclear waste from other countries, where others have made deals for the acceptance of certain kinds of waste. So there were often deals that I believe kind of went down, unfortunately, between the Russians and the United States towards dealing with excess plutonium. So the Cold War resulted in a lot of plutonium production for nuclear weapons. And then after nuclear non-proliferation treaties were drawn up and signed, there was a large reduction in the amount of plutonium that was in the end needed and therefore needed to be disposed of. And so some deals were made towards transfer of this as well. At the same time, there are also deals often with France, because France has a number of reprocessing facilities. So to give an example, again, where I'm from in Australia, there is a research reactor there called the Opal nuclear reactor. The deal between France and Australia is because Australia has no major large-scale reprocessing options. It does do some processing-based pilot work and often local work, but to do the larger scale stuff, they export their spent fuel to France, to a place called, to a facility called Leakage. It's in the north of France. And there, the French essentially reprocess the fuel. One can say they take out the good stuff, they take out the plutonium, they take out the uranium, which they can recycle into their own fuels, and they send back to Australia what I referenced earlier, intermediate level waste. So the deal essentially is Australia is not really having to deal with the high level waste coming from the fuel parts itself. They just have to deal with intermediate level waste, and so they just have to hold this waste around 100 years before it's quite safe to dispose of. So there's kind of different deals that happen around the world in this way.
Yeah. And how do they transport this in some special vessels, special ships?
Yeah, exactly. So nuclear transport is one of the most costly parts of the nuclear energy sector as well too. So there's a lot of security involved. A lot of laws have been enacted that when you want to transport or even safeguard nuclear power plants, you must have often a paramilitary force present. So if one person ever tries to say, I mean, if someone's listening and they're interested, they can try on to go to Google Maps and they can try to look at French nuclear reactors. And what often find on Google Maps is the images are all pixelated because of security. Likewise, when nuclear materials move from nuclear reactors, there is often firstly going to be a paramilitary force to make sure no one tries to do anything that is nefarious, that could cause the unexpected or bad release of radionuclides. In terms of the transport itself, you have to use authorized and very, very careful containers that can actually withstand, say, a ship taking a hit, a truck coming off the road. Another famous example too, a reference to where I'm from. After the Fukushima and particularly the Chernobyl disasters, many nuclear reactors have radioactive domes, well, not radioactive, containment domes on top of them. And these domes are designed to stop cruise missiles. They're designed to stop planes from running into them. So again, the Opal nuclear reactor where I'm from, where I used to work once upon a time, has a large kind of spider web made of concrete over it. And the idea is it works almost like a cheese grater, stopping planes going towards it. And these same kind of safety measures are often applied around all kinds of nuclear transport as well too. So there's been very, 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 very few instances when nuclear material, particularly large spent fuel transporting, there has been instances because there's so much safeguarding involved in its transport.
Mm-hmm. Are you, of course you are, but are you familiar with the term transmutation, nuclear transmutation?
Sure, of course. Yeah. So, for transmutation, people are often kind of looking at ideas of often, activating, converting radionuclides into different elements, and then also changing and also sort of splitting them as well too. So there are famous concepts of things like what are called breeder reactors. And so the idea is often you can use sort of transmutation ideas and techniques where you can actually breed out the fuel. So when you have nuclear fission and nuclear energy, you need to have specific isotopes. So every isotope, every element can undergo fission. Fission is just the process of the atom splitting. But when you want to have energy, you want to have a fission economy where you generate more neutrons during the fission process. So if you took carbon and you fission carbon, you can do this at many particle accelerators around the world. You might get some neutrons, same as some other elements. But it's not an energy efficient process. But of course, what was discovered as early as the 1930s was that, and even the 1920s, is that when you have isotopes like uranium-235, uranium-233, plutonium-239, these can fission and spontaneously then generate more neutrons and generate a positive economy. And this is the idea of nuclear fission. But another idea, of course, is what if you have a concept where you can essentially breed out new fuel? So you have an element which is called, or an isotope that's called fertile. So example people talk about is thorium reactors. And the idea, of course, is that when your neutrons come in, you can activate thorium isotopes, and then it can breed down more fuel as well too. And so recently China has announced they've actually built one of these ideas of a thorium reactor where you can actually breed out the fuel. And so the idea, when it goes down to the idea of transmutation, is you can actually start to get rid of harmful and often sort of not needed radionuclides. So one of the idea people had, and there are some very fancy concept reactors, particularly from Russia, is that you can just keep essentially fissioning all the bad radionuclides down. You can turn all the high-level waste into low-level waste by essentially just cutting down all the radionuclides by just bombarding them. It's a complicated process because in the end you want, as I say, a positive economy of neutrons, but there are concepts for this out there for it.
Perfect. We have from Canada, Kenneth Wong. In Canada, we call it spent fuel. What are your comments?
Yeah, I think in every country, the fuel that comes out of a nuclear reactor is universally known as spent nuclear fuel.
Gabriel, who pays for the waste disposal? Governments, private companies? Is a end-to-end process? Is a total cost of ownership?
Yeah.
They take care of all things?
Yeah, so there's a lot of different ways. It's very country specific because, you know, as I say, in the 1950s and 60s, everyone was very excited about nuclear energy, and people used to kind of throw up reactors. In many universities, they used to always build research reactors in the university because it was almost like a fashion. Everyone needed a nuclear reactor to do research. It was just the thing, particularly in the 60s. And not much thought was ever paid to what about the waste and the spent fuel. And this has often been the legacy issue. And this is the big issue we have in the world, is there's never a plan. But there are some countries that did actually have a think about this. So Finland was often one of the countries that, again, is pointed to because, to my understanding, they actually included a very small amount of the disposal costs in people's electricity bills. And so it's barely even noticeable, but because a portion of electricity comes from nuclear energy, and it's actually quite a significant portion, they pay a very tiny amount into a fund. And so people don't even really even notice this. But that fund is, of course, economists can invest this fund, but they can build a stable amount of money, a pot of money in the future where they can actually pay for the disposal of spent fuel, because this has often been the issue of the financial economic planning of nuclear, is the cradle to grave approach too, because in many parts of the nuclear fuel cycle, from uranium mining, uranium processing, uranium enrichment, to reactor loading, reactor operations, to nuclear fuel disposal, there are different entities involved, and they often will have their own focus in terms of how it's all paid for too. So, you know, when you look at this at the front end, this is supply based. You can look at some very large companies in the world. The names of Rio Tinto, the names of BHP, these famous large mining companies that are involved in uranium mining, yellow cake production, and then export. And then it arrives at companies like Framatome, what was known as Areva, a French company, Westinghouse, famous American company too, where they're involved then in fuel fabrication as well too. Westinghouse and themselves are involved in reactor design and reactor building and reactor development too. But then of course comes the issue too often of the disposal of the spent fuel. And this more often has fallen into the hands of government itself to ensure there is actually sort of continuity and security as well. However, at the same time, I mean, you know, people think this is just a problem to be solved. There is many industries around nuclear waste and spent nuclear fuel disposal. There are many people who get involved in finding innovative solutions, innovative planning, consultancy. It is quite a large economy in itself.
You mentioned France. I suppose, I guess that France, 70% of electricity is from, but not in Germany. Germany is closing the last 2-3. Why? It's because the fears for the waste treatment, or other issues.
It's kind of, as I say, a bit related to the intergenerational issue, in my opinion. I mean, Germany has had I don't think it had a very good communication with the public about the benefits of nuclear energy in the past. So it's extended back to the 80s and 90s. And crises like Chernobyl and particularly Fukushima have made it all the more harder. So Fukushima was the turning point for Germany. That's when they decided they would completely pull out of nuclear energy in the end. I mean, Germany itself is very, very famous. It's some of the best nuclear engineers. Otto Hahn, who was one of the first people to generate fission back in the 30s, is German as well too. So Germany has a very, very famous history of nuclear energy and just nuclear physics and nuclear science. But the communication has never been that good in terms of the benefits, and people have been skeptical. This has followed in political movements that have often stood against the issues with German nuclear too. At the other side, across the border in France, in the 80s and 90s, there were often energy problems over there too, and France took it upon themselves and they made a direct issue that nuclear will be a solution for them to get, as I say, energy sovereignty. And so when it comes to things like net zero emissions and carbon dioxide, it's really a very small issue in France because their nuclear power sector is essentially near carbon free. So they're very relaxed about this too. They're able to withstand shocks in energy markets as well because of this. Because one of the advantages of nuclear fuel is you can stockpile it. So many countries have large stockpiles of it too. The time it takes to actually use up nuclear energy is quite long as well too. So there's large stocks of this around. So when things like the oil crisis happened, as I say, the gas crisis with Ukraine and Russia, countries like France can be more protected in terms of their energy supply as well too. And this has culminated a lot of issues in Germany with energy supply. So Germany has gone down a path of going towards very strong renewables, and there's been a lot of issues around actually having dependable energy supply. And many countries, as a consequence of often seeing, you can see on the news often that they're rethinking their path towards nuclear. So some countries that were going to exit from nuclear, so for instance, Holland and Belgium are reversing their decision. They're looking towards longer futures with it. Countries like Poland are also looking to uptake a lot of nuclear. So Poland sees its net zero future coming from nuclear itself too. Likewise, there's extensions occurring in Switzerland and many other nations as well too. So again, it's a public perception issue, but when crisis comes, as I say, with energy crises, people can often see around it as well.
SMR, I mean, a small modular reactor, has a different process than the conventional plants. And how do you treat waste of this small modular reactor?
Yeah, sure. So maybe I can first say something about what SMRs are, because they're a very, very hot topic, SMRs at the moment. So, the people talk about them firstly as a very new technology. And the thing is, what it stands for is small modular reactor. And it's just a smaller nuclear reactor. And people say there's not much experience with these kind of reactors. Well, there is actually a lot of experience because most military naval reactors are actually SMR type reactors as well too. So you can look at the US at their Virginia class submarines, and they've got a few others as well too. They all run on these very smaller reactors. And the thing about these reactors is they're actually the same between the different submarines. And so they're actually therefore modular. And so, as you can see, the name goes, they're smaller modular reactors. And so the idea has come about as one of the issues with sort of larger scale nuclear is the times it takes for approvals, the costs involved with it too, and just the overall money and expenditure time. So when you build a nuclear reactor, you need a lot of approvals. You need to find a location for it. And then as you find a location, you start building it. There's several regulatory approvals that are needed. And people quote delays associated with some reactors, and often it comes down to the need for regulatory approvals. So when they first pour the first concrete, regulatory approval. When they move the containment domes, regulatory approval. And so people had the idea that there should be a way to kind of speed up these processes. And so the idea of a small modular reactor is that it's an off-the-shelf technology. So, like you can go down, instead of trying to build your own oven in your house to cook, you just go down to the shop and you buy an oven and you just have it delivered. And so it's pre-made, prefabricated, and has already passed many pre-regulatory steps as well. And so because it's smaller, it's easier to transport, move around, it's easier to construct, and as a consequence, people see it as much more of a solution as well to issues with large-scale nuclear. And so many people argue that if there is good uptake and success of small modular reactors, these can be deployed on a wider scale. You add these things together, and they can generate a good amount of energy. I hope that answers your question. Maybe I went a bit off track.
Yeah, perfect. Going to the end of our conversation to take a 30 minutes only podcast. And do not take too much time of Gabriel. The final point for me. Many consider that nuclear waste and nuclear power is the greatest invisible danger for the planet. Do you agree with that?
No, because I mean, if we look at the impacts of nuclear right now, I mean, you can compare it against what we've done with CO2 production and climate change. There is the scientific consensus currently is the Earth is warming, and this is very measurable, and this can be well tracked to the emissions since the Industrial Revolution of human activity. But if we look in the Earth in terms of the impacts of nuclear energy, of nuclear waste, there's been little on the Earth that has really been so profound as what carbon dioxide and sort of coal and fossil fuel energy has actually done. At the same time, of course, the fear of nuclear weapons is ever present. I mean, there is a line there's a strong line, red line we like to draw between nuclear energy and nuclear weapons as well too. The fear of nuclear weapons is a clear and present danger out there too. But in terms of nuclear energy, if we look at the disasters that I mentioned, Chernobyl and Fukushima, without taking away from them at the same time, Chernobyl, there was around approximately 30 deaths, unfortunately, during the reactor meltdown. Whereas at Fukushima, no one actually had passed away. Whereas from the tsunami that hit Japan during the Fukushima disaster, 15,000 people were killed as well too. And so there is often an over focus, I think, at nuclear itself too. And at the same time, there are many solutions for the waste as well. I mean, I often point to the fact that nuclear is one of the few energy technologies where people do think hard, long about the waste. And when I mean long, they think 10,000, 100,000 years. No one thinks very long enough about CO2, since every car outside is producing CO2, and where it ends up in the environment, ends up in the atmosphere. But all spent nuclear fuel is captured. All nuclear waste is always captured and contained as well too. So when people say it's the biggest threat, I find that a bit hard to accept, since there are clear and present dangers currently out there.
Yeah, interesting. Let's plan other podcasts with Gabriel, and please, audience, send questions to the LinkedIn, and we can invite him again to more specific points. And I'm not specialist in this area, so my questions are very generic, and so that's the point. Thank you, Gabriel. It was a pleasure to meet you.
It was a pleasure. Thank you very much.
Thank you. Have a great day.
You too.